Okay, so in 7.2, we're going to learn how to verify solutions of differential equations and kind of just discuss what a solution is in this context. So first, let's write down some examples of what differential equations might actually look like. Because in day one, all we really did was learn how to model differential equations from phrases. Okay, so here I've written the same differential equation in all three notations that you might come across. And these might kind of remind you of when we did implicit differentiation, where sometimes we would have the derivative show up in our equation. So that's kind of what I want you to think back to today when we're working with these types of equations. So basically, how do we solve this? Well, a solution to a differential equation is a function or a class of functions that make these particular statements true. It is not a value or set of values, which is what we're used to seeing with equations. So let's actually start with that type of problem, and then we'll try to make that connection to what's similar about it and yet what's different. So first, we're going to solve this quadratic equation, our favorites. So of course, the first thing we have to do is factor. X squared plus 2x minus 35. 35's nice. I know it's 5 and 7. And we have leftovers that are positive. So 7's positive, 5's negative. And so we get two possible solutions. It could be positive 5 or negative 7. Now, what I'm asking you to think through is how do we know or verify that these are in fact solutions, right? Well, one thing you can do is substitute them back into the original problem. So for instance, let's take x equals 5 and actually substitute it back into x squared plus 2 times x minus 35 equals 0, right? If I plug a 5 in here, I'm going to get 25 plus 10 minus 35. And I'm verifying that that does, in fact, give me back the original solution, which was 0. Okay. We could also do the same thing, but with x equal negative 7. So if we plug in negative 7, the same thing hopefully will happen. And we get 49 minus 14 minus 35. Does that make a true statement? Yes, it does. So what's going to be similar with a differential solution, equation solution, versus an algebraic equation solution is the way we check it. We can take what we suspect the solution is and simply just substitute it in and see if it gives us a true statement. That's exactly what we're going to do. What's different is what we're plugging in will not be a number. It will be a function of some type. And similar to how here we can have more than one solution, that can also happen with differential equations. So that's why it says it's a function or class of functions, meaning more than one function might work. So the most common way you'll see this is with this first type of example. So basically they're giving us some sort of differential equation right here. And they want us to see which of these functions makes that statement true. So you'll notice you need two things to test here. They give you y. All of these are the original functions. So for each of these functions, you need to find the second derivative. Now, some of them you might be able to have a hunch, but for this first example, I'm going to work through all of them. Okay, so let's go ahead and find the second derivative for a. So we know that the first derivative of e to the x is very exciting. It's just itself. And then the second derivative is also e to the x. Starting out easy here. Okay, so let's try plugging this in. So I have e to the x plus the original function. Does that equal 0? It does not. He's out. Let's try the next one, e to the negative x. So for this one, remember, you have the chain rule. So it is its own derivative, but then we multiply it by negative 1. So really we're getting negative e to the negative x. Then for the second derivative of that, it's going to happen again. So we're going to get this same function back, but times another -1 because of the exponent. So it's just going to give us back a positive e to the negative x. So this time if we plug it in, we get e to the negative x, that's the second derivative, plus the original function. Does that equal 0? No, it does not. So far, right, these were our checkpoints here of plugging it in. It does not give us true statements. Let's try some trig. The first derivative of sine is cosine. The second derivative would be the derivative of cosine, which is negative sine. So if we plug that in, that would be negative sine x plus sine x. Hey, does that equal 0? Yes, it does. So this is a possible function that is a solution to this differential equation. Now there may only be one, but we're going to check the rest of the options and make sure, because it says choose all that apply. So negative cosine x, be careful here because the derivative of just cosine is negative sine, right? So if we have negative times negative sine, that's going to just give us positive sine. And of course the derivative of positive sine is simply cosine. So here we're going to get cosine x plus negative cosine x. Oh, that's nice. That means we have a second possible solution. All right, now let's get into some chain rule. So I'm going to do my scratch work at the bottom, but I'll probably just write the simplified answer up here. So if we derive sine, we get cosine 3x, and then the derivative of the inside, 3x, will give us an extra times 3. So altogether, it's going to become 3 cosine of 3x. And then when we take the second derivative, the 3 out front stays because it's a constant multiple. The derivative of cosine is negative sine. And then the derivative of the inside again is another 3. So now we have a 3 times a 3 times a -1. So altogether that's going to become -9 sine of 3x for the second derivative. Okay, and so for this one I'm not feeling particularly hopeful. We have -9 sine of 3x plus the original function sine of 3x, and that one definitely is not 0, so he's out. And this brings us to the last one. So again, the 3 out front is just a constant multiple. Derivative of cosine is negative sine, so it becomes -3 sine x. So then the second derivative becomes -3 cosine x. So I have -3 cosine x, oh okay, plus 3 cosine x, so this one is another possible solution. So in this particular case, out of just the ones we looked at, there were 3 different functions that were a solution or made this differential equation true. Okay, so the other way you might get a question having to do with solutions of differential equations is one that is a little bit more vague. So what they've done here is given you a function y equals 7e to the ax, and they tell you it's a solution to this second order differential equation. So basically, if we take the second derivative of this, it should somehow be equivalent to 9y. So let's go ahead and start that process. So dy dx would have to equal, well, it's exponential, so it is its own derivative, and the 7's a constant multiple, so it stays out front. Then we have the chain rule with the exponents. The derivative of ax would be times an extra a, so we could write it, well, I don't know if it's that important we simplify. Well, no, I like to. Sorry. Can't make up my mind. I like having things that are constants on the front because then I remember they don't really play into the derivative. Okay, so the second order derivative would be very similar, right? This is just going to remain where it is. Or, well, actually, the whole thing remains the same because it's exponential. And then times a for the chain rule. So we get 7a squared e to the ax. Okay, so now we look at this second piece of information. So we know this to be the case. So we have our second order derivative here. So I'm going to say 7a squared e to the ax has to equal 9y. And they want us, going back to the actual question, it says find all values of a such that this is true. So we're going to try to solve for a, but this is a little weird because I've got a's and x's and y's. So one thing that we said yesterday was that sometimes the original function can show up in the differential equation. And when you see that happen, especially in something like this where it's just a lot of stuff going on, one way to simplify it is try to see if this original function is floating around somewhere in your derivative functions. So in this case, I think we could definitely find 7e to the ax. So what I'm going to do is move the a squared out front, and then I can separate out the part that I am going to rewrite as the original function. So this part right here is actually the part we started with, right? So instead of keeping it in the complicated form, I'm going to rewrite it as y. Okay, and you can see why this makes our lives so much nicer, because those cancel out. And so we're left with a squared equals 9, and so a equals plus or minus 3. If a is plus or minus 3, then this relationship will be true.